Based on those grammar changes, of course, we're going to change our exp data type to have tylam and tyapp. So instead of writing big lambda or something like that, we'll clarify that it's a type lambda extraction. And instead of an @ sign, we'll call it a type application. A type lambda abstraction that has a name for the argument, right, to the big lambda, and it has a body expression. And in an application, we have a function and we have an argument. And the new thing for this argument is that it's not an expression, it's a type. Meanwhile, we need some way to represent the polymorphic values, the things that are expecting a type before you can get to an expression inside. So we'll use polyv for those. And you'll notice that polyv doesn't mention the argument name. That's because by the time we're interpreting, we don't actually need to work with the types. So we can just ignore the type argument that comes in. But then as soon as a type is supplied by a type application, then we can start evaluating some body expression. And of course, we need to keep an environment with that expression as a value. Finally, we add to our type grammar here, our type data type, we add IDT to represent the arguments of a for all. And then we have a for all where it has a name and a body. And of course, the body is a type, not an expression. Let's look at how this works out on some examples. So if we parse this expression, this curly expression now with big lambda, then clearly this is a tylam e. But when we interpret, because that's what our test is doing, then we should get a polymorphic value, something that's waiting for a type. And as soon as it gets a type, then it evaluates this body expression. So we see that lam e is the body expression is inside there, and the empty environment, because we don't have any bindings around this. All right, so the polyv doesn't have to keep track of the quote A. We'll see how that works at the type checking level. If we have a big lambda like this, and then we apply it to a type, now the type is going in for quote A, and we can get just the lambda back. So in this case, when we evaluate the lambda, then we'll get a closure, right? So just like being under a lambda delays the evaluation of expression, being under a big lambda delays the evaluation of its body expression until a type is passed in, but here we've passed in a type, and that's why we get the closure out. If we then take that closure, so these square brackets have the same code as before, but now I've added a curly brace to apply that result function, that result closure to the number 8, then of course 8 goes in for x, and we get just 8 out as the result. Let's look at the type side also. When we're parsing a for all expression like this, again, these little quote marks in curly syntax are just little bits of syntax to say it's a type variable. We don't have to remember the actual quote mark, so a for all turns into a for all t, where this quote is at the plate level just to make the symbol A. So this is a polymorphic type, a for all type, parameterized over A, and then the body of that polymorphic type is arrow. Right? It's an arrow from A to A. So that's why we have an arrow t from IDTA to IDTA. And if we type check, so instead of interp now, we looked at this at interp. Now if we look at type checking this big lambda expression, it's big lambda parameterized by A, so we expect a for all parameterized by A. And then inside the body here we have a function, so it's going to have an arrow type from A to A, so that's why we have an arrow t from IDTA to IDTA. If we type check this expression, so here I've got, if this is my whole program, I've got a lambda with an x that's supposed to be some quote A, but we don't have a big lambda wrapping it around it. So this is a free type variable, and that should go wrong at type checking time, just like free regular variables and expressions go wrong at interp time. So this free type variable will be rejected, will cause the expression to have no type. If we could parse this lambda though in an extended environment where we do have a meaning for A. So remember, type check has a type environment. What we're going to need is a TID constructor here to say this type is defined. We can't say what it stands for because the abstraction hasn't been applied yet. But you could imagine that we get to this stage by having a big lambda quote A around it. So big lambda will need to extend the type environment to say that there is such a type A. And then if there is such a type A, then we'll be allowed to say that the lambda expression has arrow t IDTA to IDTA. And this is where that kind of thing would come from, right? So big lambda will need to put TID A in the type environment so that we get the arrow type we just described, but then that's how it's able to put it all together to get a for all a arrow t type as a result. And then if we do a type application, then at type checking time, we need to do a kind of substitution. We need to take the for all type that we get here, and @ sign will make sure it gets a for all type, and then it's got an actual type, and it substitutes in the actual type for the for all argument. So all the IDTAs turns into numt here because we applied that polymorphic value to a number